Light has fascinated scientists and philosophers for centuries. Isaac Newton himself believed light was made of tiny particles, but eventually experiments revealed light's wave-like behavior.
Wave optics explores how light, acting like a wave, interacts with itself and the world around it. Imagine ripples on a pond. When they meet, they can either reinforce each other or cancel out. Light waves do the same. This interaction is called interference.
Polarization is another key aspect of wave optics. Just like ocean waves that move up and down, light waves also have a direction of vibration. It's why polarized sunglasses can block glare and why three-dimensional movies work.
Wave optics underpins many technologies we use every day, from lasers and cameras to fiber optics and medical imaging.
Understanding wave optics unlocks a deeper appreciation for the beauty and complexity of the universe. Have you ever wondered how soap bubbles create those mesmerizing swirls of color? This visual symphony is due to a phenomenon called thin film interference.
When light strikes a thin film, part of the light is reflected from the top surface, while the rest travels through the film and reflects off the bottom surface. These two reflected waves then interfere with each other.
The colors we see depend on the thickness of the film and the wavelength of light. If the two reflected waves are in sync, they create constructive interference, resulting in bright colors.
Conversely, if the waves are out of sync, they cancel each other out, resulting in destructive interference. This leads to dark bands or the absence of certain colors.
Now let's consider what happens when the thin film is not uniform in thickness but instead gradually changes, forming a wedge shape.
When light shines on this wedge, we observe a pattern of bright and dark fringes called interference fringes. These fringes follow a specific pattern. As the thickness of the wedge increases, the path difference between the reflected waves also changes, leading to alternating bands of constructive and destructive interference.
The spacing between the fringes depends on the angle of the wedge and the wavelength of light.
Wedge-shaped films have practical applications in optics. They are used to test the flatness of surfaces such as mirrors and lenses. By observing the interference pattern, we can detect even minute deviations from perfect flatness.
Wave optics has led to numerous practical applications that have revolutionized our world. One such application is the development of anti-reflective coatings.
Have you ever noticed a faint purplish or greenish reflection on camera lenses or eyeglasses? That's an anti-reflective coating at work. These coatings reduce unwanted reflections and glare, allowing more light to pass through the lens.
Anti-reflective coatings work by exploiting the principles of thin film interference. A thin layer of material with a carefully chosen thickness and refractive index is applied to the surface of the lens. When light strikes the coated surface, the reflected waves from the top and bottom of the coating interfere destructively, cancelling each other out.
Another important application of wave optics is in determining the flatness of surfaces, a crucial requirement in many optical instruments. This is achieved using a technique called interferometry, which relies on the interference of light waves.
Unraveling polarization, the many faces of light. Light, as we know, is an electromagnetic wave, meaning it consists of oscillating electric and magnetic fields that travel through space.
Polarization refers to the direction of the electric field's oscillation. Most light sources, such as the sun or a light bulb, emit unpolarized light, which means the electric field vibrates in all directions perpendicular to the direction of travel. However, light can be polarized, meaning the electric field oscillates in a single plane.
This can happen naturally, such as when light reflects off a smooth surface like water or glass. It can also be achieved artificially using polarizing filters. There are different types of polarization, including linear polarization, circular polarization, and elliptical polarization.
Linearly polarized light is the simplest form, where the electric field oscillates along a straight line. Circularly polarized light, on the other hand, has an electric field that rotates in a circle as the wave propagates. Polarization plays a crucial role in various technologies, including sunglasses, LCD screens, and optical communications.
Malu's law quantifying polarization. Now that we have a grasp of polarization, let's delve into a fundamental law that governs its behavior, Malu's law. This law, named after French physicist Étienne Louis Malus, describes how the intensity of linearly polarized light changes as it passes through a polarizing filter.
Imagine shining a beam of linearly polarized light onto a polarizer. The polarizer only allows light waves whose electric fields are oscillating in a specific direction, called the transmission axis, to pass through. Malu's law states that the intensity of the transmitted light is proportional to the square of the cosine of the angle between the polarization direction of the incident light and the transmission axis of the polarizer. Let's consider a numerical example. Suppose we have a beam of polarized light with an intensity of 100 watts per square meter. If we pass this beam through a polarizer whose transmission axis is oriented at an angle of 30 degrees to the polarization direction of the light, the intensity of the transmitted light would be 75 watts per square meter.
Double refraction light's split personality. In our exploration of wave optics, we encounter a fascinating phenomenon called double refraction, where a single ray of light splits into two rays when passing through certain materials. This intriguing effect is most prominently observed in a crystal called calcite.
When a beam of unpolarized light enters a calcite crystal, it is split into two rays, an ordinary ray and an extraordinary ray. The ordinary ray obeys the usual laws of refraction, while the extraordinary ray does not. This difference in behavior arises from the anisotropic nature of calcite, meaning its optical properties vary depending on the direction of light propagation.
The splitting of light in calcite can be explained by Huygens' principle, which states that every point on a wavefront can be considered as a source of secondary wavelets. In calcite, the speed of light is different for the ordinary and extraordinary rays due to the crystal's anisotropic nature.
Double refraction has several practical applications. It is used in polarizing prisms, which are essential components in various optical instruments, including microscopes and polarimeters.
The future is bright wave optics and beyond. Wave optics has come a long way since its inception, and its future promises even more exciting discoveries and applications. Researchers are constantly pushing the boundaries of our understanding of light and its interaction with matter, leading to advancements in fields such as quantum optics, nanophotonics, and advanced holography.
Quantum optics delves into the quantum nature of light and its interaction with atoms and molecules. This field has the potential to revolutionize computing, communication, and sensing technologies by harnessing the principles of quantum mechanics.
Nanophotonics focuses on manipulating light at the nanoscale, smaller than the wavelength of light. This field is opening up new possibilities for developing ultra-compact optical devices, high-resolution imaging techniques, and novel materials with enhanced optical properties.
Advanced holography aims to create more realistic and immersive three-dimensional images by recording and reconstructing not only the intensity, but also the phase of light waves.
While wave optics has made remarkable progress, challenges remain in its application. One challenge is the development of more efficient and cost-effective manufacturing techniques for complex optical components. Despite these challenges, the future of wave optics is bright, promising groundbreaking discoveries and applications that will shape the future of technology and our understanding of the universe.